I'm going to start the recording. Let me make sure I got enough memory. 2 hours and 18 minutes. We won't use that much today, don't worry.
Have you graded our test?
That's a good question. No.
No.
But I thought about it. But I will grade it soon.
I also have it.
Oh.
That means within 2 weeks. Don't listen to him.
What's that? Audric is he's saying it'll be at least 2 weeks, but the physical proximity of a student makes it makes me do it quicker. So that's the other downside to doing online courses with me is I forget your existence. No, I need to grade it soon, obviously, because there's not much semester left. I mean, comparatively speaking.
Do you guys end around the same time? I think we end the 28th.
Whew. Man, I don't remember.
That sounds about right.
It's about
around the time, but
yeah.
Yeah.
Any event. Oh, I'll begin with a word of prayer. So, Heavenly Father, we thank you again for your grace to us and your mercy each day. I pray that you just guide our work today. Help us to glorify you when we do, Lord. In your name I pray, Lord Jesus. Amen. All right, so let me get into it here. So I thought we were done with chapter 3, but I think that it's important to talk about this theorem, and because it's kind of the basis for a lot of stuff that goes on in chapter 4. Theorem 3.7.7, this is the Riesz representation theorem. All right, so let F be bounded linear functional on Hilbert space. H, then there exists a unique x naught in H for which f of x is equal to the inner product of x with x naught. What was a Hilbert space?
Complete. It's a normal linear space with a nice dot product.
Right. So what you said, it's a complete inner product space. That's right. And then we can use that inner product to induce the norm. So you're also right about that. So yeah. Moreover, we have the norm of f is equal to the norm of x naught. Now, I think I should probably talk about some things here. What do we mean linear functional? Right, yeah, vectors, sure. So it's mapping from H to the field. Let's suppose it's complex, just for giggles. All right, I mean, it's either the complexes or the reals here. But yeah, that's what a linear functional is. Now, to say it's bounded, what's that mean?
That the norm of
Mm-hmm.
the linear mapping is estimated to some alpha
Mm-hmm.
or x, but in the domain such that the
Oh.
norm of x is 1.
Ah, very good. Yeah. So there's the two ways we could either do that, like you said, it's bounded on the unit ball.
Or just do the norm of x times alpha.
Right. M times. It's the same alpha?
Oh, well, I mean.
Yeah, I guess it's the same. It's the same alpha, right? Yeah.
It's linear functional. It's
Like that.
linear mappers, we would
Yeah.
say, yeah.
And this is just for all x and h, right?
Right, yeah.
But these are equivalent notions. So either you bound it on the unit vectors or you bound it for all the vectors in this sense. Right? It's not bounded, really. I mean, when I think of something being bounded in the discussions before this point, earlier in math, when I say something's bounded, it means I can put a number above it and that's it, right? But this isn't quite that, right? It's like, well, there's a number times the input, the length of the input. So it's already a more nuanced idea of bounding than our first exposure to boundedness. But yeah, that's the Riesz representation theorem. Let me, before I get into the proof, let me just give you an example of this. So example, we could look at H equal to the complex n vectors, right? And we could look at the mapping that's a projection map. So like this, you input x1, x2, xn, and let's suppose that I'll do it just like the book does, picks out a particular component, x of n naught. All right. So that's one of these guys. The n naught is somewhere between 1 and n. So in this case, this is, it's easy enough to verify that this is a linear functional, and also that it's bounded, right?
Are you using example 3.71 as the definition of linear functional?
Example 3.71?
Oh, wow.
Yeah.
I didn't see that.
Ah, what page is that on, Audric?
132.
Oh, that is a linear functional.
Yeah, like I don't know. I don't know if he's just defining a particular one.
I'm talking about example 3.73 at the moment.
Okay.
3.7.
So linear functionals can be assigned. They're not.
It's a mapping. I mean, it's a function, so there's a lot of different ways to define one.
They talk about functionals on page 29 at the
Here, we'll look at that other example in just a second, okay?
Okay.
Let's finish this one. So here,
I was looking for a definition of it.
oh, the definition is just this. A linear functional is a mapping from the.
Oh, okay.
This is more general than Hilbert's.
Yeah.
This is even more general than Hilbert space. A linear functional is a mapping from the vector space to the field.
Yeah.
Okay.
Yeah, it's on page 29 as well.
Oh, page 29?
Yeah,
Okay.
it's just exactly what you said.
Yeah. So if you look at this, what is this? Well, this is exactly the inner product of x with the unit vector that has 1 in the n naught spot, en naught, right? Where en naught, the ith component of that is Kronecker delta n naught comma I, right? It's this guy. The standard basis. And then that's the usual inner product in Cn, right? How's that defined?
It's just taking, it's like multiplying.
Yeah, we do.
Transpose qualifier.
Yeah, transpose times the conjugate of this one, right?
Right.
But that is literally just x transpose, times en naught, because it's real, which just picks out the n naught component by linear algebra, So there you go. Sometimes I think this is called the Riesz vector. X naught is sometimes called the Riesz vector. I don't think he says that, but I remember that from somewhere else. So then what? What else can I say about this example? Is it clear that it's bounded? I mean, it's clear. Well, it's certainly clear that f of x is equal to the inner product of x with en naught, right? So that illustrates it. And I guess the other question here is, what do we mean, how do you define the norm of f? What's that, how is that defined? Maybe that's something we need to talk about again.
Well, that's the supremum, right?
That's exactly, that's the supremum over the norm of x equal to 1, right? Of what?
Just the norm of f of x.
Norm of f of x, right? So that's the supremum sup of the norm of x equal to 1 of, well, it looks like the modulus of x and naught, right? And the largest that x and naught can be, think about this. If we're talking about a unit vector, what's the largest that a component can be in magnitude? Can you have a unit vector with like with a component with magnitude 2? No, right? So every component of a unit vector has to have magnitude less than or equal to 1. Like in fact, when the supremum is realized is exactly when x is equal to e n naught. See that if I have e n naught is equal to x, this implies that x n naught is equal to 1, and x sub j is equal to 0 for all j not equal to n naught. So in fact, when the supremum is realized, in fact, its maximum is attained, is explicitly when we evaluate at the Riesz vector. But anyway, this is equal to 1. Which is also equal to the magnitude of E n naught, yeah. Which is the x naught here. So this is how this all works together. Now the other one, the non-example that Audric was looking at, is probably worth talking about for a second. Example 2, what was it? F of x equal to
the interval from a to b of x of t dt.
Oh no, that one's good. That one's an example.
Okay.
I was trying to find a non-example. I think 3.7.2 is it's a functional defined by f of x equals to x of t naught. Now here, f is a mapping from what? From h to, I guess, the complexes where h is what?
It's L2 of AB.
L2
Sorry, yeah.
of AB?
Yes, yes.
So that means that x is a mapping from a comma b to the complexes, right? And here, t naught is an element of a to b, is that right?
Yeah, fixed point. Yes.
He says, all right. He says the functional is linear. Do you guys see why it's linear?
Well, it's just the Lebesgue interval is linear functional, right?
What's that?
The Lebesgue interval itself is a linear functional.
Oh, no. It's simpler than that. Why is f linear? If I take x plus, say, a constant times y, what do I get?
Yeah, f of x plus c f y.
Oh, fixed point. Okay.
Right? So I get x of t naught by definition of, function addition, right? Pointwise defined function addition, which is what you said, Audric. It's f of x plus c f of y, right? So therefore f is linear. F is linear.
You said that was like that rule of function addition.
Yeah, pointwise defined. How do I add the function? X and y are functions, right? And c is a number. How do I, take a function x plus a scalar multiple c times the function y? How is that defined? Well, it's defined by the pointwise evaluation rule, right?
Okay.
Yeah. I did it in college algebra before break.
You said it again by
Yeah, just definition of function addition, yeah. So it's linear, right? Why isn't it bounded? So yeah, what's the norm here is one thing I should probably, I think the norm is actually given to us back in, oh, and that's not square brackets, these are like so, my bad. Right? I think. Anyway, so what was the, oh, that's not the norm? Curses, what's the norm on this thing? I've forgotten.
The L2 norm?
Oh, excuse me, what was the inner product on this? What did we say? It was FG was what? Wasn't it integral from A to B of f of t, g bar of t, dt? Wasn't that it? And so like the norm of f in this case would be, oh, and I shouldn't be using f here, my bad. X and y. I'm thinking about x and y and f differently, yeah? F is the linear functional, x and y are the functions, which the linear functional is eating. So like the norm of the function f, at x rather, it's the square root of the integral from a to b of x of t, x bar of t, right? So to decide whether or not this linear functional is bounded, I should be looking, I mean, there's two options, right? Like you guys were telling me, I can either go with option 1 or option 2, right? If I go with option 1, it begs the question, what are the unit vectors in this space, right? So the unit vectors, if we have the norm of x equals to 1, what's that mean? That means, yeah, exactly. Integral from a to b of like the absolute value of x of t squared is equal to 1, right? That criteria describes unit vectors in L2AB. So as you think about, you have a unit vector in this sense, right? And then you take x, you take f of x is equal to x of t naught, right? Why is that not bounded? I mean, the integral works out to 1. If the integral is 1, doesn't that mean that the functions have to be bounded? What I said sounds plausible, doesn't it? Why is it wrong?
What's above like you have it raised to the power, then 1 raised to the power?
Yeah, 2.
Okay.
That's just 2, because x bar is the absolute value squared.
Yeah.
That's all that's going on there. Nothing too fancy. So like to look at number 2, I need the norm, right, of f of x, which is the norm. So it's literally the complex modulus of that, right? That's supposed to be, I'm supposed to be able to do what? Put a, you know, less than or equal to question mark, what? Some alpha? And, oh, that's it, right. So how, I mean, why can't I pick? Why can't, I mean, so there's a more precise question. Why does such an alpha not exist?
Does alpha have to be greater than 1?
No.
Well, yeah. Well, the xt naught has to be 1, right?
I mean, alpha could be 0, I think. But
Yeah,
what? What's that?
Oh, wait, never mind. No, that doesn't hurt our case.
We're talking about Lebesgue integrable functions, right?
Yeah.
So if I make x of t naught bigger than, you know, like suppose a given function integrates to 1, right? Then I take the value at t naught and I make it into a kabillion. Is the integral still 1? The only thing I've changed is the t naught. Remember, so the integral does not care about the value of a function at one point.
No.
We're talking about the Lebesgue integral. I know that if two functions are equal almost everywhere, and they would be if I take my original x, which has area 1, right?
Yeah.
And I take my modified function where I take x of t naught and make it whatever it was before, forget about that. Instead, change it to a kabillion, to use a technical term.
I see. So you can make it as large as you want.
See, I can make,
No longer pick it.
yeah, I can make x of t naught as large as I want, and I haven't changed the integral being 1. Therefore, this can't be bounded. To do a less Lebesgue kind of thing, to be a little bit more kind of less, you know, abusing that property kind of proof. If you think about tent functions, you can make tent functions arbitrarily steep between a and b such that the area under them is 1, and yet they're as high as you want by just making it as narrow as you want. Yeah, in the limit we approach the Dirac delta, but before you get to that, in some sense, those tent functions have arbitrarily high values, and yet their area is bounded. So bounded area does not imply bounded function in this sense. Yeah. So anyway, but yeah, the one right before this was an example, Audric. If you just integrate the function from a to b, that does define a bounded linear functional.
Yeah.
And actually,
So
mhm.
what the theorem's saying is that there exists in particular that an x naught such that it always bounds the function.
Let's see, the other one was integral from a to b of x of t dt. Sorry, Audric, I was.
Yeah.
Yeah, no, I'm moving you.
Well, I was talking about the theorem. All the theorem stating is that there has to exist an x naught which the norms are equal.
There has to exist an x naught which makes the operation of the functional tantamount to just taking an inner product with a fixed vector, which I've called the Riesz vector.
Okay.
So like this one here, f of x equals, let's see, the other example, we had f of x is equal to the integral from a to b of x of t dt, right? He says that defines a linear functional on the Lebesgue integrable functions from a to b, right? And I think this one's interesting to look at too, since we're still having a little bit of trouble understanding the idea of what it is. So let's look at another example. So he says if x naught denotes the constant function 1 on AB. So if we say x of x, like say x naught of t is equal to 1 for all t in AB, right? Then clearly x naught is an element of L2AB, right? And if we look at the inner product of x with x naught, what do we get? We get the integral from a to b of x of t times x naught of t conjugate dt by definition, right? But this is exceedingly silly because that's the constant function 1. And so this is literally just the integral from a to b of x of t dt, which is f of x, right? So it does satisfy the inner product thing, and it is Now, I mean, why is this linear functional bounded?
Because no matter your choice of t, you still get a 1.
Doesn't matter your choice of t.
Like x naught of t is a constant function, so you can pick t as big as you'd like, still 1.
But I'm asking why.
Or any x.
What I'm asking is why is the norm of f of x? Let's work again with definition 1 of bounded for f. I'm talking about the boundedness of f. So why is f bounded? Well, we're assuming, let's assume that the norm of x is equal to 1. All right? And then f of x, what is the norm of f of x? Well, we're talking about the norm of what? Good grief. The absolute value of the integral from a to b of what?
Well, f of x is
Oh yeah, so how do I calculate the norm of that integral? I have to take the, this is a complex number, right? So I take the modulus of it, I think. That's the norm, right?
yeah, sorry. Yeah.
But what does it mean to say that the norm of x is 1? What is the norm of x? How is that defined?
So that's that one more time.
What does this mean, norm of x equals to 1?
The norm of x equals to 1, yeah, it means that that the magnitude of the vector is 1, or if you want to think about it like that, or
Like this, right?
Yeah.
If I square it, I get that, right? What does that mean, though, here? That means here that the integral of x of t, x bar of t from a to b dt is equal to 1, right? In other words, the integral from a to b of x of t, absolute value, squared dt is equal to 1. I mean, we do have a theorem for integrals, right? The absolute value of the integral is less than or equal to what? The integral of the absolute value, right? So it's almost there, you know. It's square down there, you know.
Oh, and we have max we go back to t is greater than 1 r. I was gonna say, and that won't work.
Well, isn't the
How about this? I'm going to do this. I'm going to square this.
Oh wait,
I'm
the
gonna
norm of x of t is always 1.
I'm going to, well,
Never mind.
but that's what this means, the norm of x being 1. X is a function. That means this integral is 1.
Right.
So if I square this, I square this. Then I also have this squared, yeah?
yeah.
But I think you can argue
Well, if you have the below condition, never mind.
mm-hmm. I guess that's my question at the moment. Can you relate the integral from a to b? Let me use a different letter, g, let's say. You know, g dt versus the integral from a to b of g squared dt. You're given that g is positive, right? Or non-negative anyway. Like, And of course, this is squared, right?
I mean, is there any properties of sums that we could use? Like just change the integral to sum?
I'm just asking, like, intuitively, which one of these is bigger?
You gotta think. Well, let's see. If you set it to a constant function, right, or a non-trivial constant function, you get
Just saying G equals to C for the sake of discussion. Cool.
yeah.
So C times B minus A.
That would be.
I think they're going to be equal in that case? I don't know.
I don't know. No, actually, no.
Versus,
That'd be CB minus CA, right?
versus this, right?
Yeah, right.
Yeah.
Sorry.
And so one would be C squared and then the difference product.
So you've got B minus A squared versus C squared B minus A. So I guess the question is B minus A larger than 1
Yeah, more or less.
or less than 1? And of course we're taking absolute value, right? So you don't, I mean, well anyway, but oof.
Yeah, because that is just like, there's a theorem, if we have like the absolute value of x of t is greater than equal to 1, then we say absolute value of x t is less than equal to this absolute value of x t squared, and then there is a theorem that integral
Yeah.
if f of x is less than equal to g of x, then integral of f of x is less than equal to integral of g of x. I don't know.
I was thinking maybe you could use, yeah, that product, that the inequality product theorem thing, yeah, maybe. I don't know.
For
I don't
some
know.
reason, having f of x equal to the dot product between x and x naught implies bounded.
Oh, good point, Audric. How is that? Good point. We don't need to do all this, do we? So I'm down in the weeds. But we don't need to be down there, do we? Because we could use the theorem that we're ignoring, which related the inner product to the norm, right? So let's... I am curious what the missing link was there. I feel like we were close to it, you know? But, all right, let me move on here. Let's look at that idea, Audric. Come on. So we've got, the question is, what's the norm? Well, not the norm, right? What's the absolute value of the inner product of x and x naught? Do you guys remember? Less than or equal to? Remember this? Cauchy-Schwarz. Right, so that's the norm of x times the norm of x naught, right? And so, and this is the norm of f of x on this side, right? Oh, there it is. That's definition, that shows it's bounded. This is bounded definition 2.
Okay, so, yeah.
Right, we're using,
Norm is,
we have, you know,
it literally is it, okay.
and the alpha is what? Where the alpha is, yeah, this is our alpha. Ah.
Thank you, sorry.
No, it's fine. And I think that is actually also, we can calculate alpha here, right? I think it's like the square root of the absolute value of b minus a. Is that right?
Square root of the value of b minus a.
It's like the norm of x naught is supposed to be the square root of the integral from a to b of x naught squared dt, but this is the square root of b minus a. So, I mean, it is taken for granted that b is greater than a in all this discussion. Otherwise, you know, it's annoying.
I think they said that.
Yeah,
did say that.
they say it somewhere. If they didn't say it, I wouldn't fault them. Okay. Now, the proof of the Riesz representation theorem, I best resist the urge to go over. If you look at it, it does use the other things we haven't really covered deeply. In particular, it uses this lemma 3.75, which says that if f is a non-trivial bounded linear functional in a Hilbert space, then the dimension of the null space of F, the perp to the null space of F is one-dimensional. And so that like sets up a projection formula in his proof of the Riesz representation theorem. And so I don't think the proof is terribly hard. It's just we should go on, okay? It's more important to me at the moment that you know what the Riesz representation theorem is than you know its proof, okay? And he has a name. The element x naught corresponding to a functional f is sometimes called the representer of f. just representing. Sorry. I may have been reading too many of Peter's jokes lately. Oh, do you know about this, Audric?
I don't think I want to.
You don't know about my nephew Peter sends me jokes. I've been reading them to my classes. Peter's 10 or so. I forget his exact age. I'm an uncle. I'm allowed to not know these things. If you don't know the age of your own children, it's generally frowned upon. But I feel like a nephew, you're allowed some amount of ambiguity, right? Is that fair, Audric? What do you think?
What's fair?
Some amount of ambiguity and understanding of nieces and nephews' ages. Like, I think you have to know the age of your own children, but I think you shouldn't be required to know the ages of nieces and nephews. I feel like that's...
I don't think you should be required to know the age of your children either.
Oh, really?
Yeah.
Ooh.
You've met the threshold. I think if it's 3 or over.
Oh. So once I have 3 kids, they gave me the right to forget birthdays? Or no, the fourth one is where I gained the right.
You have to remember the dates, but not the age.
Ah. Remember dates, but not age. Let's see. I like it. I like it. Okay, so let me go on here. So the reason I wanted to talk about this Riesz representation theorem in part is because it sets the stage for similar theorems in chapter 4. And so I think it's important to mention so that you're not kind of like, I want you to see that this is the first example of a more general idea. And so, okay, so section 4.2, so we're in chapter 4 now, which is on linear operators on Hilbert space, all right? So, chapter 4. Linear operators on Hilbert space. So a linear operator is just a linear transformation, all right? Maybe just use the word operator because oftentimes the examples that we're looking at are function spaces. And typically a function of functions is called an operator. For example, the differentiation operator. You feed it a function, you get out a new function, right? So there are many examples of operators that are discussed here. I should mention he likes using A for the operator. I like using A for matrix, but whatever. So if A is the operator from H to H, all right, then the norm of A is defined to be what? It is defined to be the supremum of the values of A taken over the unit ball, right? Supremum of the norm of x equals to 1 of the norm of AX. This is the definition of the norm. All right. This is also known as the operator norm. What does it mean to say A is bounded? We need that the norm of AX is less than or equal to some constant K times the norm of X for all X and H, or that it's bounded on the unit ball, right? So 1 or 2, like we were just talking about. So what's the difference? Like, I suppose the difference now is we're talking about there's a big change between now and 10 minutes ago. Now we're talking about functions from H to H, right? The linear operator goes from H to H. Before we were talking about linear functionals, right? Which is a mapping from H to the field. Big difference, right? So he rattles off a bunch of examples here, like the identity mapping on H is a linear operator. The zero mapping on H is a linear operator. You know, if you take a scalar multiple of the identity, it's a linear operator. And then his example 4.22 I think is worthwhile. So let's talk about this one. This is essentially, hey, let's do 10% of linear algebra in an example. Here you go. So you have a linear transformation on Cn.
You sure you don't want to change that A as the operator?
If you'd like, I can make it a T.
Yeah, let's try
T? All right, sure, why not? And so that's a linear transformation on complex n space, all right? So what does that mean? Well, if you want, we can calculate T of EI, right? And I'm glad you said that, Audric, because now you've given me license to use A as I like to use it, which is that this is the sum.
I saw that coming.
Okay, this is sum j equals 1 to n of A J I EJ, I think. Let me think about my life here for a second. That should be the ith column of the standard matrix. Yeah, we're good. So the j varies going up and down the column, I is fixed. So this is actually the ith column of the standard matrix. All right? So but this is a definition of AJI. I mean, there is others, but this serves to define the matrix for the linear transformation, right? This is the definition of the standard matrix, if you like. What happens if we take the inner product of this, right? What happens if we take the inner product of T of EI with, let's say, EK? What happens then? Well, notice that the summation is in the first slot. So we have straight linearity of the inner product there. Therefore, we can pull out the summation, and we can pull out the numbers. So we get the sum, j equals 1 to n of AJI, inner product of EJ with EK. But that is what? Remember, these are the standard basis, right? And this is the standard inner product for Cn. Yeah, this is Kronecker delta, right? And so what you're really looking at here is straight up A. Now J was a variable of the summation, so that gets gone. And we keep the K. K is a free index. It's over here as well. You got to keep the K. So we get ourselves an A, K, I.
And so, why does the first slot have the nice property, but the second slot doesn't?
That's the definition of inner product, is that the second slot has the conjugate linearity.
Oh,
That's like,
yeah,
I think
yeah.
the first problem, that's like in homework for chapter 3.
Oh, that's the first homework problem in chapter 3?
It's a simple problem.
All right, so what do we have here? We have then that all right. So this is true, great. So then the next thing he does, he's like, let x equal to the sum over I of, say, lambda I EI, right? So take a typical n vector in Cn, and then feed it to Tx. What is T of x equal to? Well, it's equal to um, sum over I, right, of lambda I times t of ei, right? But that's equal to what? That's equal to the sum over I of lambda I, sum over k, right? Of a, I did j. So sum over j of aji ej, right? So putting these things together, what do I have? I've got t of x equal to the sum over I and j of lambda I, and I'm gonna trade this a sub ji for, well, I don't know if I should do that. I was thinking I could convert it back to inner product. Maybe I shouldn't do that though. So it's this times what? Times a ji ej, right? I just wrote it again, basically, but now he points out that if you take the inner product of tx with, let's say, you know, I'll use a k here just to be different, then what happens is you just get what? The sum over I and sum over I of lambda I a sub ki. Why is that? Because the inner product of ek with ej is what? It's Kronecker delta kj, right? So when you take the inner product of tx with ek, you just get that. Anyway, these are all calculations we can do. What are we? Mm-hmm.
Sorry, what was you said the sum over ei, ek was what?
Is it, can you see it? No?
Yeah, I can see it. Okay. Oh, I see. I didn't get the Kronecker delta part. I got you.
Oh yeah, I'm sorry, I was too far to the left or too far to the right, I don't remember. Probably too far to the right, you know how I am. Let's see here.
Funny.
Yeah. It's a good
So the question then is, I mean, we're assuming it's a linear transformation. Is it bounded?
It's a finite sum, right?
Yeah, these are finite sums, right?
Cool. Coach Schwartz would give us bounded, wouldn't it?
Yeah, let's see here. Yeah, fair enough.
What's the norm of TX? Well, we know the norm of
Yeah. I mean, you could even just use this down here, right? Like, see this equation here?
Yeah.
Or, I mean, just take the, just take the norm.
You're saying the sum of the lambda?
If we just take the norm of this right here, right?
Yeah.
We have that the norm of tx is less than or equal to, you know, the sum over I and j of the norm of lambda I, aji, ej, right?
Yeah, but then you can pull that lambda out, right?
Well, lambdas, these are numbers. That's a vector. It's a unit. It's a unit vector. Like this is simpler. I'm getting to something. Just give me.
Lambda would
That's right, because, well, this is literally equal to the absolute value of lambda I times the absolute value of a sub ji.
I thought it was inequality.
I don't, yeah, let me think.
No, it's a property of the norm throughout the
But the thing is,
read the AI and say,
but I thought if we had a constant, right, the norm of a constant times a vector, it's equal to the absolute value of the constant times the norm of the vector, right?
yes.
So if I think of,
I like the definition, yeah.
if I think of all of this stuff here as the constant, and if I think of e sub j as a vector, that's reasonable because these are constants and that's a vector.
Yeah.
So I have this times the norm of ej. Well, the norm of ej is 1. So that's gone. Now, okay, so
Yes, that's definition of a norm. Yeah, definition of a norm, you have to be able to plot scalars over a field.
right. And then there's various ways to go here, but if we, well, I mean, here's one. I see it immediately if I do this, right? So if the norm of x is equal to 1, that implies that the absolute value of lambda I is less than or equal to 1 for all I. See, because remember, lambda I is the component of x in the standard basis. So you cannot have any lambda I larger than 1 and still have x being a unit vector. So with respect to that condition, the norm of t of x is what? It's less than or equal to the sum over, let's see here. I guess I can leave the I and j for a moment. I'm not sure I really need that though. Absolute value of ji. Well, yeah, I guess I do. Like that, yeah.
Oh, okay.
And
That's a sort of,
there's your alpha.
yeah.
I mean, there's your k. This is the quote-unquote k, right? Because the other way to do this is that the norm of ax is less than or equal to k for all x and h subject to the norm of x is equal to 1, right?
And what are we defining as the absolute value of the matrix?
Well, this is the absolute value of the jith component. So it's not a matrix. It's
Okay.
yes, the beauty of the component notation. But hey, that's just a box of n numbers, complex numbers, and you can take the sum, and that whatever it is, right? So there you go. Now he's got something a little bit different. He's got that the norm of a, he has that the norm, oh, well this is, I guess I don't know what the, hold on a second here. What does this tell you about the norm of t itself? See, because that at the moment is just a bound on the, I mean, that shows that t is bounded. It doesn't tell you what the norm of t is, though. Because remember, the norm of t should be...
There's this, the super norm, yeah. But just, isn't there just the set of, the norm of t of x is less than or equal to, well, k that we have there, isn't it probably that implies that the supremum of the norm of t of x is less than or equal to the sup of k? Or is this just
Oh, okay.
k, right?
So you think this says that the norm of t is equal to k? That seems wrong.
That's quite,
Oh, it's less than or equal to. My bad.
yeah.
So the supremum of the norm of x equal to 1 of the norm of t of x, right?
Oh, yeah, but we're just trying to sort of,
Yeah, and so that would have to be, the supremum is what? It's the least upper bound, right? So
of the sets of those,
so this does have to be less than or equal to k. I think you're right about that, but that's not quite what he has. See, he has he says it's less than or equal to the square root of the sum of the squares.
What the components?
Yeah, well, I mean, he says that the norm of t is less than or equal to the square root of this guy.
Yeah.
Sum over I and j of the norm, excuse me, the absolute value of a, I guess he does ij. It doesn't matter, ji, ji, whatever.
Yeah, his alpha ij is your aij.
Yes, exactly. Precisely, aij is equal to alpha ij.
Yeah. What you wrote there, you just add a square to it, or you just norm it, essentially. I mean, yeah, but why is
And we'll have the components are less than
why do you
one.
have to take the unit? Why do you have to square it and square it then square root it? Is like you saying take, like, from what I understand.
Oh, I think I don't think he's wrong.
Value.
I don't think he's wrong. This is also true, but I think we derive this, which is true.
Yeah, but the only like, if as long as we suppose that our sum is positive, we're fine. Like, it's the same exact equation, is it not?
No, I don't think so. No.
But it's square rooted, isn't it?
No, it's the square, it's not the
But it's
square of the sum, it's the sum of
the
squares.
square root of, it's still, square root's not linear. So, no, they're different, but I do think they're both true. But not for the same reason. Not for the same reason. And if I had to wager, I would suspect that, man, I want to say, all right, let me see if I can find my way to this. So if we take the absolute value of t of x, inner product with ek, right? That's less than or equal to what?
Norm of tx.
The absolute value of the norms of each.
Yeah. Does that help? See, because this was the absolute value of the sum of lambda I. I guess that's, I'm not sure this is helpful. Because this is equal to that, right? So that's less than or equal to the norm of t of x. Just a second, let me just think through this here. So what's the norm of t? The norm of t is equal to the supremum, right? Over the norm of x equal to 1 of the norm of t of x, right? But that is literally the supremum of norm of x equals to 1 of the norm of the summation, right? Of how's it go? I mean, my stupid formula gone too. There you go. I and j, lambda I, AJI, EJ, right? But instead of doing the triangle inequality like we did last time, all right, just straight calculate it.